Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I'm very pleased to have Jim Davenport with us today. Hey, Jim.
Hello, how you doing, Frank?
I'm doing very well today. It's actually going to rain a little bit in Phoenix today. So,
Oh, that's fun.
well,
It's unsurprisingly going to rain here in Seattle.
yes, if you told me it was going to be sunny in January in Seattle, I'd be shocked.
We had a little bit of sun. We actually had a little bit of sun during the AAS meeting last week, and that was nice because
Ah,
after the sessions, you could actually go outside. And
nice.
after spending all day in your basement, like I was, it was nice to go outside.
Yeah, I was there. I was in the AAS publishing booth covering people coming by and asking various questions about the journals or
Mhm.
um,
I
so
was I was shocked to hear about the journals maintaining sort of a steady level of publication during this pandemic. That's really surprising to me that people have been that productive and the journal's been chugging along, which it's encouraging to hear.
yeah, I mean it was kind of a mixed bag. There were some people who had more time on their hands,
Hmm.
uh, less committee work or something, whatever it was, and so they were able to push their articles through or get going on one. Other people find themselves with additional duties. So in the end, it was kind of a wash. And yeah, for 2020, we hit roughly pretty close to previous publication year. So
It's
um,
cool.
yeah. Hey, I have to say I'm a fan of your YouTube channel.
Thank you. I've been a fan of the things that the Double S YouTube channel has been doing. It makes me happy to see like every week a new chat. Oh my goodness, somebody's trying to call me.
Real life, we love it.
Real life. There we go.
There you go. So actually, I've been doing a 3-day release schedule. And so it's been a mix of authors,
Hmm.
it's been a mix of the scientific editors. It's been a mix of lately. I've been doing Sky and Telescope as well, so trying to bring in the amateur astronomy community. Um,
What was the impetus to get this started? I guess that's what I'm curious about. Like, was it just that we didn't have the opportunities to meet each other, and you're just trying to put more astronomers forward, or is this something that's been sort of been in your mind before the pandemic even?
good question. Okay, take a few minutes to answer that, so bear with. I guess it was about 2.5 years ago. I created a talk, a presentation on publishing the AAS journals as an author. And so I gave that talk a few times. Like I would go to places and I would do the science colloquia, and then usually there's an astronomy seminar, and so I would do that one to let people know how things work on the author side of the house. Um, and so I was sort of evangelizing for the journals, and I got picked up on that. So the AAS wanted me to evangelize a little bit more. So I looked around, and I noticed that they had a YouTube channel, and that YouTube channel was actually started in 2016. It is lost to the sands of time who started it. And so I looked at it, and this would have been circa March 2019. And so it had been in existence 3 years. It had all of like 5 videos. It had like 6 subscribers. And I was going, we ought to do something with this. So that's when I started. So the 2-year birthday is coming up here in March 29. And so originally, basically for the first, almost the first year, I concentrated exclusively on the journals. So for example, you will find the talk on publishing the AAS journals as an author. I did a set basically on how to be a good referee, the business model of the journals, why we do anonymous, what are the options for double anonymous.
I really liked your history of the Double S Journals videos too.
Did
I think that was excellent and
right,
informative.
histories. So it was pretty much journal focused.
Hmm.
Um, and so at the end of that first year or so, we come up to from 6 to 329 or odd subscribers. Um, and so talking about the journals proper, like anything else, it's finite. You can only, okay, I've said everything I can say about them. So I was looking around for other things to do, and I didn't want to compete with AAS Nova, with Susanna Kohler's stuff. And so I was poking around, and the idea came up, well, why not talk about the authors, right? So instead of the journal, sort of a thing, right? And so really the impetus was, well, there's a lot of people behind this. So why don't we bring the people out? Why don't we bring the community out? So why don't I, and so by doing, the idea was, okay, I'll do an interview with somebody and I'll talk about their actual article. So that doesn't really compete with AAS Nova because that does something different. That's a print medium as well. And so the first one of those went off in about March of 2020. And it just so happened that that's when the pandemic started. There was no plan for that to happen. It was just me shifting, expanding the scope of the channel. As it turned out, there was a captive audience all of a sudden. So there was a little
Very
bit
fortuitous, yeah.
Yeah. But people, it seems to be going well. We just clicked over 1,000 subscribers right before the AAS, so it's going pretty well. People seem to like to talk about their papers, and not unsurprisingly. So yeah.
So I had one idea that I wanted to throw out there,
Yeah.
just something that it struck me as being a cool thing that could be an addition to the channel, which
Yeah.
is there must be a wonderful archive. I hope there is an archive of plenary talks. I mean, I know for many years we have filmed them and they do get posted to members. And it's something that I've wondered, like, maybe not every plenary talk, that's a ton of content. I mean, or maybe just post every plenary talk. I don't know. That's easy. But there have been, at least in my mind in the last decade, a handful of like truly spectacular plenary talks. And it makes me wonder if that's a ready source of content to like sort of play the hits and go back and play some of the most impactful or most interesting or engaging talks. Could be a really great thing to post to the world now that they're sort of out of the digest of things that people are trying to get out of the meetings.
Yeah, no, that's a great suggestion. And we need not do a big content dump all at once. You could
Right.
drizzle out the plenary talks, I don't know, once a month, 2 months, something like that, so it's not this big dump.
Right.
No, that's a great suggestion. I will. I don't have those videos, but I know people who probably would, and so we'll have to check. And there may need to be some conversion in some cases from physical.
Yeah, I'm not sure what format they're actually stored in on the AAS website side. I don't know, but
VHS tape beta.
yeah. Every time you click on the link, it spins up the tape.
Yeah, no, that's a great suggestion. Thank you for that one.
Yeah.
Yeah. So Jim, what do you like to do for research?
I like to do lots of things, but almost anything related to stars and time domain astronomy has been sort of my bread and butter for a long time.
Cool.
I thought for a while I was going to study, like when you're young and you think you know what you're going to do. I thought for sure I was going to study things like Sloan Digital Sky Survey and big surveys of the sky. And then this mission called Kepler launched right when I was in the midst of grad school, and sort of midway through grad school, midstream, I said, I don't want to do this. I'm spending all my free time playing with these light curves from this Kepler mission. Clearly, that is a sign that I don't want to work on this survey stuff, and I want to do this Kepler stuff. And so I dropped it all in like my fourth year, and completely changed over. And I've been there since. I've been working on Kepler and now spending most of my time working on its predecessor TESS.
Cool. And of course, there's some future missions coming on that. Plato's coming up. That would be great.
And meanwhile, you find ways to mix in the old loves. Like you do get the old survey stuff in there. You try to mix in that's the great thing about the era we're in right now, is that all the surveys can play together. That we can play with Gaia and we can play with upcoming surveys like LSST and it's all very exciting. It's a good time to be a data hungry time domain astronomer.
Awesome. Which will bring us to this really lovely AJ article. 10 years of stellar activity for GJ 1243. Jim, take us away.
Yeah, so this is the star that converted me, as it were, from being a stellar cluster and stellar populations astronomer to a time domain astronomer. And it was this active M dwarf. It's an M4 star, so it's about 20% the mass of the sun. And it's fairly close by. I should know off the top of my head how far it is. It's something like 10 or 11 parsecs. It's pretty close. And very thankfully, my thesis advisor, Suzanne Hawley, and her more senior grad students, had applied for this guest observer time on Kepler 10 years ago, when it was in sort of its first calls for guest observer time. For this, they just tried to get any good nearby active M dwarf they knew of, and this was just one of them. And it wasn't a particularly special star. For their, it hadn't been the subject of a lot of papers from the group before, but it was known to be active. And this was the light curve that when I saw it, my brain just kind of like melted. And I said, "This is amazing. This light curve is that Kepler produces just spectacular." So let's just jump down to the light curve, just because words, words, words. But let's actually look at Figure 1, because this is the TESS light curve here.
Awesome.
And so this is two sectors. So TESS has these sort of 27-ish day pointings, whereas Kepler was stationary for nearly 4 years. So Kepler's light curve is very long, whereas TESS has these sort of short snapshots by comparison. Now, short snapshots, 27 days of data without interruption, except for this sort of mid-sector gaps there in the middle. Each of these would have been a monumental undertaking from the ground before Kepler, before TESS. So each of these light curves themselves I'm old enough to remember that these are phenomenal products in their own right.
Oh yeah, this amazing.
Yeah, there's no sun doesn't rise. There's no gaps from cloud rays. Just constant monitoring. You get this continuous and complete census of what's going on from the star. And what blew my mind, what totally wowed me, was you could see this sort of sinusoidal modulation, which is here sort of shown in the blue.
Yep.
And you could see this really frequent flare activity. These impulsive, explosive events just going off constantly. And it's like reading something out of a textbook about what we see on the sun. Is you get to see that the star is spinning and there's these dark, cool spots on the surface. Here you can see that there's actually two spots. So you can see that it's a sinusoidal modulation with kind of a double dip in the bottom. And this is two spots that are sort of at this point in time separated by, I forget how far in longitude. We'll be able to look at that later. And then these flares, and the flares I think are actually, for this star, the most interesting thing. And so as a PhD student, I dropped everything and I wrote two papers on this, one about the flares and one about the star spots. And that sort of formed the core of my thesis.
Cool.
And Kepler had a wonderful legacy, and then unfortunately could no longer point at this field of view. And so we lost track of GA 1243. We've been able to observe it again from the ground. We've done some other follow-up campaigns, but we've never had this kind of continuous, beautiful monitoring again until Enter the TESS mission. And here, 10 years later, we're getting a look back at GA 1243. So for me, this paper is a really personal labor of love, that I wanted to come back to the star that really shifted my focus and really transformed my career. And so in some respects, it's like we're playing the hits here. We're like, I want to go through and do all the things that I did, 5-10 years ago. But I want to do it with this new data. And TESS is not, quote unquote, as good as Kepler. It's a smaller telescope, so the data has more noise. So there's more sort of fuzz here, and these flares are a little smaller amplitude, and the spots are a little harder to see. But it's still really amazing data. And so here we've just gone through, and it was like being back in grad school. I had to spin up the code that we had used. We used this code, we called it FBI, called Flares by Eye.
Yep.
Which was code that I had to dust off and figure out how to work on my new Mac laptop that I hadn't used in years. But we went through and ran this, and it worked exactly like the Kepler data, which was great. It was able to remove the star spot modulations and help pick out the flares. And then we went through one by one and just made sure to manually adjust when the flares started and stopped, because these things can be hard to pull apart. Some of these flares are small amplitude. Some of them are massive.
Yeah. Little tiny ones.
Yeah, you got little tiny ones in there. And yeah, when paging through the light curve, it's like an extremely boring video game. You sort of page through this light curve sort of half day chunks, and you make sure that you're not picking up cosmic rays or just, little spurious fuzz. But you go through and you collect this data set, and here, out of just two sectors of test data for this very active star, you've got 133 flares that we are able to posit. And there's probably, a handful more flares that we weren't able to pull out from the data that are sort of confused with the noise. But 133 flares, and I had friends a decade ago writing a PhD thesis on samples that were smaller than this, which is just really amazing. So, this is a really wonderful snapshot of a couple of months of this star. And so the goal was to go back and look at this star to see, had anything changed? Had anything substantively changed? We could go back and do the same kind of like demographics of flares here. Now the flares don't look exactly like they did in Kepler. So if we scroll down to figure 2, so I mentioned TESS is a smaller telescope. Instead of a sort of 1 meter class telescope, which Kepler was, TESS is a much smaller facility. It has camera lenses that are sort of more akin to the size of my coffee cup here. They're about 10 centimeters across. So your signal noise automatically is going to shrink or is going to make the flares a little harder to detect, especially the small amplitude ones. But on top of that, TESS has a broader and redder bandpass filter. So they both use these really wide white light filters, optical filters. But Kepler here in blue is bluer. It's more like a really wide R band filter, whereas TESS in red is like a really wide I. It's like I plus a little bit of Z. For those who remember the STSS filter band passes. So it's really wide, which is great because TESS wants to observe M dwarfs. And so you can see here in gray, this sort of template spectrum, and in black, I think this is actually like I forget where the spectrum came from. It's from the PMSU catalog from Neil Reed's work from the 1990s here.
Okay.
There's this flux calibrated spectrum here in black.
Mm-hmm.
But you can see that this TESS bandpass is right in the middle of like where all the flux is coming out for this M dwarf. Whereas in Kepler, you're still in sort of that blue.
Yep.
It's blue for an M dwarf. It's still pretty red if you were looking at a solar type or a hot star. But for the M dwarfs that TESS wants to study, and so TESS is a great facility for studying M dwarfs, you get a lot of that flux. So this star looks great in TESS. But the flares are very blue events. Flares have characteristic temperatures of 10 to 20,000 degrees in a black body sense. And so these blue events really in this red bandpass, you're only getting just the tail of the event. So you're just seeing the tail of that flux. And so there's not a big, so a small flare in the TESS bandpass might be a 6 magnitude flare in U band or something. Could be a massive flare. So there's a funny trade-off here. This facility is really good at getting very precise light curves for M dwarfs. So, okay, it was built for transiting exoplanets, which is why it wants to get this wide flux. But it's difficult to pull out the really small amplitude flares. So that's one of the interesting differences there. And so these competing factors mean that TESS is a really good platform for doing this kind of work, just like Kepler. But the flares are a little smaller amplitude and a little bit harder to gather. So they're not exactly the same looking events, but they're pretty similar. And one thing, if we scroll over to figure 3, that we were very pleased to see, and we sort of expected, is that the flare rate is about the same between Kepler and TESS. And so it's a little bit of a confusing diagram. This is a characteristic figure we use. We call it the flare frequency distribution, or FFD for short. And it's a backwards cumulative distribution, which is always confusing. And so to talk this out, this is saying that at a given energy, say 10 to the 33 ergs, there are what it looks like about 1 flare every 10 days or something like that. 0.1 flares per day at that energy or larger. So you read it in the reverse cumulative sense. And so once you go down to say 10 to the 31 ergs, there are 10 flares per day at that energy or larger.
Got it.
And when you sum these things up, so you're summing them from largest to smallest in this cumulative diagram, what you see is this, like many things in nature, you get this power law. You get a straight line here. This is it's on log energy on the X, and we've used a log scaling on the Y. And so you get this sort of power law diagram. So there's very few big flares and lots of little flares. And we see this on the sun as well. We see this over 10 orders of magnitude and amplitude of flare energy on the sun. And this right here gives you a lot of the story about the difference between the missions. So there's error bars both in the X and the Y. There's error bars in X because that's a signal to noise measurement. So if you've got better signal to noise, bigger telescope, you're going to have smaller energy error bars. And there's error bars in the Y direction because those are counting errors. And so the more you add to the bin in this cumulative diagram, the smaller those error bars. And this provides this kind of funny bow tie shape where you're most precisely determining something in the middle. They're around 10 to the 32 in this case.
Okay.
Those have the best errors in X and Y. And so that's the best place to kind of measure the slope of that power law. And you can see the black and the blue data very simply lay on top of each other. And I gave a talk last year about this figure, and my title was "This is Boring." And that's interesting that over a decade time scale, these two things look like they're drawn from the exact same line, that there's just a same power law, nothing has changed.
Okay.
And that's telling us something fundamental about the star, that this power law tells you something about um, the self-critical organization of magnetic fields and how active regions can clump together, and whatever that process on the surface is that makes some flares big and some flares small. That process has not changed,
Okay.
and the total magnetic field output of this star over 10 years hasn't changed. Probably not unexpected. This thing is young, something like 50 million years old. It's rapidly rotating. It's got a strong magnetic field. So we don't think that it should change. Like, there's not a big prediction like, oh, this M dwarf should have changed a lot. But if we bring it close to home, the sun has about a factor of 10, about an order of magnitude change in its magnetic field output, specifically in flares, over a decade timescale. Over the sort of classical 11-year solar cycle, you go from activity maximum to minimum,
Right.
and you get a factor of 10 modulation in the flare rates per day.
Mm-hmm.
And so this is the best star to start this work, to start this look about. We have a 10-year time scale, and this is the star with the best flare sample. In Kepler there, that's 6,000 flares. That's the best sample of flares ever amassed for a single star. And with TESS, you get this great snapshot. And you can see 10 years later, nothing has changed. So there may be activity cycles. There may be variations in the flare rates for these M dwarfs, but we can at least positively say here, they're longer than 10 years. They're longer than the baseline that we have.
Yep.
And so again, this is a very boring figure in the sense that this is just two lines lying on top of each other with big error bars. But I think that's interesting. And my hope is that opens the door. I'm jumping ahead now to the future, but I hope this opens the door to doing this kind of work for G stars and K stars and things that have dynamos that are a little bit more like what we see on our own sun.
Yep.
So that I'm really excited about.
Nice.
So that was half of my thesis, revisited for this star. And then if we scroll down to figure 4, we can see the other half of the thesis, which has also been, I think, this may, I think, be one of the most impactful parts of the Kepler legacy. And that is the study of star spots. And so this is kind of, some people call this like a river plot, where you have time on the x-axis and you have phase or equivalently longitude around the star. And we're wrapping the light curve here. And so the color or the darkness of each pixel corresponds to the relative flux level of the phase folded light curve. And so we're seeing this is like the phase folded light curve dynamically over time. And so the left 80% of this diagram is the Kepler data. This is 4 years of the Kepler light curve for GA1243. And you can see there's a dark band traced by these orange dots. These are our star spot models.
Okay.
And this dark band is this primary star spot that seems in the rotating frame of the star to be fixed, roughly fixed in amplitude and fixed in phase, or equivalently longitude. You can see this at the same time. I thank you for zooming out. You can see this sort of simultaneously in the phase folded diagram here at the bottom, here at figure 5. This is the star spot that's fixed close to phase of 0, or equivalently phase of 1. And so we get a really precise anchor on the rotation period, because with Kepler, you get 4 years from that first data point to the last data point, and you can phase fold that and get a really precise measurement. This thing rotates in about 14 hours. So it's whipping around really fast. You get a lot of foldings over 4 years. We come back with a 10-year baseline. Now we extend that baseline and TESS 6 more years. And when we try phase folding the TESS data with the Kepler data, you can even more precisely update that rotation period, assuming that star spot has not changed in longitude. And that allowed us basically another decimal point of precision. So we get to, I think, a part in a million, something like that, six significant figures. So we really know the rotation period of the star very precisely. And that too says something very simple and very powerful about what's going on the surface of the star. So these star spots are big. They're probably bigger than the biggest star spots that we regularly see, the sunspots that we regularly see on the sun. but they also live a very long time. So this primary star spot, we have a little bit of ground-based data that we looked at in my thesis that predates Kepler. So the signal noise is not great, but you can see that primary spot is kind of there too. And so we can say from this data, it's 10-year time scale, but we have another roughly 10-year anchor. So we know for at least 20 years, that star spot has been in place on this star and roughly the same amplitude. And that is unlike anything we see on the sun. Sunspots live days, sometimes weeks. In very rare cases, the big ones will survive a few months and will come around a couple times.
Right.
And so these are very big, very long lasting features on this star.
Yeah, particularly given that fairly short period.
That's right. That's right. And so those are probably correlated things. That the fact that this is rotating so rapidly means that it has an extremely strong dynamo, which means that the magnetic fields are really stable. And so the sun, thankfully for us, has a fairly weak magnetic field. This thing has a really strong magnetic field. So that's probably why it's so stable. But that has all kinds of impacts. That strength of that magnetic field means that you've got a lot of resistance to like shearing on the surface, and such as differential rotation that we see quite prominently on the sun. In the sun, the equator rotates about 5 days faster than the poles of the sun. So the sun's equator is moving quite a bit faster than the poles. We don't know exactly the latitudes of these star spots. We have some guesses, but we think there is a lower latitude spot. And so here in figure 4, that's the sort of purple dots.
Yes.
And when we chop up the data and we try to estimate the longitude or the phase of these spots, we get sort of rough estimates of where those things are. And these features kind of blend together. And this is not a perfect deconvolution of these two sort of sinusoidal features. But we get a rough estimate of where these spots are. And we see these times when the secondary spot seems to emerge and decay. So you see sort of like clumps of this spot activity around day 200, day 500 in the Kepler data. And you see periods where it seems to undergo nearly linear evolution. And so those are kind of highlighted in this sort of cyan band that we've wrapped around in phase space here. These sort of periods of nearly linear evolution. And we take this to be a sign of another very long-lasting, very long-lived star spot, a secondary spot, probably at a lower latitude, probably differentially rotating, but differentially rotating really slowly. So probably 10 times or slower in terms of shear than we see on the sun. So this is a very rigid rotation, nearly solid body rotation, but there is secondary features that are very slowly moving. And so when we come back 10 years later, and I think this, I mean, I should say up front, I think this is sort of coincidental, but it's really interesting. When we come back 10 years later and we take that cyan line that we sort of roughly trained on those purple dots from Kepler, and then we do the same kind of measurement of where the two spots appear to be, the orange spot is roughly right where it should be. It looks like it might sort of modulate in phase a little bit. But those purple dots, okay, it's only 3 spots, but they lie right where we expect that secondary star spot to be if it continues to be long-lived. And so we can say that we think there are 2 spots, both bigger than what we see on the sun, both very long-lived. And this is, again, very stable configurations of magnetic fields. So there's some large sort of dipolar or quadrupolar arrangement on the surface that is very slowly changing and seems extremely stable. So this is, I think, a direct opportunity. I would want to say challenge, a direct opportunity for people who do dynamo modeling or sort of magnetic field topology models, which I know there's a lot of work going on in the stellar community and also in the sort of giant planet community. There's a good challenge here to take something like, can you take a Jupiter-like dynamo or a fully convective M-dwarf dynamo and make a model where these spots live this kind of time scale with this amplitude and this level of stability? This seems like a really special test case. Now, this rotation and this sort of spot modulation and spot evolution has been seen on lots of stars. This is a rapid rotating M-dwarf. But the future of this work, I think, is really powerful. TESS is going to measure, so Kepler measured something like 30 or 40,000 rotation periods. K2, in a paper that came out just today on the archive and is submitted to the AAS journals by one of the grad students here at UW that I'm working with. We've extended that sample by at least another 10,000 from K2, and TESS looks to all respects like it's going to at least double that sample. So we're going from an era where maybe, when I was first an undergrad, we had rotation periods from spectra for maybe 1,000 stars.
Mm-hmm.
And now we're in an era where there's at least 50 to 60,000 rotation periods sitting on my hard drive. And there's another 100,000 coming in the next several years from missions like TESS. And then the promise of Gaia even could extend this to hundreds of thousands, maybe even 500,000. So we've gone from knowing the rotation periods of a handful of stars, often in tidally locked kinds of configurations,
Right.
to knowing the rotation for hundreds of that, for huge ensembles of nearby stars, and even in some cases being able to trace pieces of the surface topology, surface features over time, over now a decade time scale. This is starting to approach the kinds of things that we see on the sun. And so when you start to make those kinds of time scales and predictions of things that you see on the sun to things you see on other stars, I think this is a huge opportunity. So
Absolutely.
one of the things that I'm most excited about in the next few years is going back to anything that we've got years baseline on from TESS and from Kepler or other missions, but going back with TESS now and revisiting any of these stars that had activity measurements in the 70s and in the 80s, revisiting any of these stars that had rotation, sort of possible rotation signatures or spot evolutions that we're seeing in the sort of 80s and 90s, and even the early 2000s. And now we're going to have this really precise anchor from TESS. So we're going to have this beautiful look at these stars, which is going to be, I think, the foundation of stellar activity measurements and therefore solar activity or the solar stellar connection for
Right.
decades to come. I think it is the best time to be a stellar or a solar astronomer because the data is just so powerful and overwhelming.
Awesome. Yep. Very cool. It's going to have a lot of implications on the types of models that are done. And at some point, as that baseline seems like it would continue, you might be looking for examples of things like glitches or the disappearance of spots and then how quickly it's back. And you may not get it for one star, but much like stellar evolution, you'll be able to piece it together from 100,000, 200,000 stars, and you'll get a sense of what the evolution of the magnetic field would be.
Exactly. Also, there's all this foundational work from like Erica Bomba-Tens from decades ago about activity timescales versus rotation timescales, and we're at the precipice of being able to constrain that, which is really cool. From light curves alone, right? From statistics alone, which is great.
Mm-hmm.
Yeah, it's a huge opportunity, and then you mix things like Gaia into this, and it's just, again, there's never been a better time, I think, to be a stellar astronomer.
Yep. The future is going to be really cool over the next decade or so on new topics. So it's really great. Jim, I want to thank you so much for spending some time and walking us through your really lovely AJ article.
My pleasure, Frank. Thanks for having me on the channel.
You're welcome. Goodbye, everyone. We'll see you on the next one.